Hallo, it's dumplet here. Here's an item on number theory. M and n are positive integers such that m divides 2n plus 1 and n divides 2m plus 1. Find all possible ordered pairs mn. Credits to the Art of Problem Solving community for this item. As usual, pause this video if you'd like to give this item a try. But if you're done, let us dive into the solution. So here we have a symmetric divisibility. So what this means is that, for example, if mn works, then I can interchange m and n so that nm would also work. And we're going to see some application of this in a while. But first, let us try to make some observations based on m and n. Now, usually, whenever you have an item like this, we try to see, well, aside from the divisibility, we can try to make some bounds. Because maybe there is an upper bound or a lower bound for the values of m and n. So the most basic thing that we can get from this one is that, well, because m and n are positive integers, and if this 2n plus 1 is divisible by this m, then we must have m must be less than or equal to 2n plus 1. Because obviously if m was bigger than 2n plus 1, then it's impossible for 2n plus 1 to be divisible by m. Now we can have the same reasoning for for n. We're going to get n is less than or equal to 2m plus 1. But this doesn't really give us a very nice result because, yes, I can kind of restrict one variable by fixing the other, but we can try to make, we can try to do better here, because here we're given with two divisibilities, and from these we can create actually another one here. So from here, since m divides 2n plus 1 and n divides 2m plus 1, I can say here that mn, the product, should divide, obviously, the product of these two. Because, well, 2n plus 1 has a factor of m, and then 2m plus 1 has a factor of n, so this should be correct. Now, let us try to expand this and see what we can do here. We're going to get 4mn plus 2m plus 2n plus 1. So if we expand this, we're going to get 4mn plus 2m plus 2n plus 1. And from here, actually, we can get that since, well, mn divides 4mn plus 2m plus 2n plus 1, this part is already a multiple of mn, so we can ignore that part. We can just say that mn is going to be divisible by 2m plus 2n plus 1. So technically here we have 1, 2, and then the third divisibility here. And with similar reasoning to these two, we can now form an inequality for this. We're going to get that mn, it must be less than or equal to this 2m plus 2n plus 1. Now here, it's better than the original thing we have here, because technically speaking, these two are, I'm going to say they're both degree 1, because they're both linear, so m and n. Same here for the n and the m here. But here we have something of degree 2, so mn, a product of two variables, and here we have something linear on the right side. So it is expected that if m and n grows big enough, at some point mn would be significantly bigger than these two. So this suggests that we are going to do some bounding for the values of m and n. And this is actually not that difficult to find because it's just a bounding. So we can actually make some observations here that, well, let's try to see when is mn pretty close. I'm just going to say equal to. When is it equal to or pretty close to this 2m plus 2n? Now, we can just do some trial and error here. And you guys kind of see that 4 give, like, if m and n are both equal to 4, it is pretty close to 2 times 4 plus 2 times 4. Actually, it's the same, actually, so 16 is equal to 16. So maybe the upper bound for m and n, it's close to 4. So let's try to make some observation. Maybe we want to set m and n to be greater than 4, because we realize that, well, if m and n are both equal to 4, it seems to be that mn is pretty close to the value of 2m plus 2n. Now let's try to consider this one, which is in effect m and n being greater than or equal to 5. Let's see if we can kind of disprove this case or something. So, well, if m and n are greater than or equal to 5, let's try to see if mn is greater than 2m plus 2n plus 1. Now, how do we verify this, though? It's just a matter of kind of factoring using the Simon's favorite factoring trick. Now, let's try to put this to the other side. So we're going to have mn minus 2m minus 2n being greater than 1. And from here, I can do the factoring by adding 4 on both sides. So from here, I'm going to add 4 to both sides, so plus 4, and then plus 4. And I can factor the left-hand side using just factoring by grouping, or this is just a result of the Simon's favorite factoring trick. I'll get m times n minus 2 minus n times n minus 2. That's going to be greater than 5. Now this left side here, I can factor it as n minus 2 times n minus 2. And here we made the assumption that m and n are greater than or equal to 5. Now that's going to give me m minus 2 is going to be greater than or equal to 3, and n minus 2 is greater than or equal to 3, so the left-hand side has a minimum possible value of 9. And since 9 is going to be greater than 5, well, we can finally say that, well, if m and n are both greater than or equal to 5, this inequality would be true, so mn would be greater than 2m plus 2n plus 1. Therefore, this cannot be the case since we want the other sign. We want the less than or equal to sign. With this, we can get that at least one of m and n is less than or equal to 4. So it's impossible for both numbers to be greater than or equal to 5. So that's the bound. And all we have to do is just kind of list down all the possible values now that we have an upper bound for at least one of m and n. Now with this, since we have a symmetric equation, let's just say, without loss of generality, let's just say m is the smaller one. So since m is the smaller one, it cannot be greater than or equal to 5. So it's just 4 cases to check. Checking m equals 1, m equals 1, 2, 3, and 4. Now actually we can do a little bit better here and immediately say that 2 and 4 are impossible because, well, m equals 2 and 4, that's going to give m to be even, but 2n plus 1 is always odd because it is 1 more than an even number. So 2 and 4, they're impossible for m. Anyway, so let's try to check m equals 1. Now if m equals 1, the first one is obviously true, so we just kind of worry about n. We're just going to worry about m being divisible, n being divisible, n being divisible by 2n plus 1 becomes 3. That gives two values of n, the two values of n equals 1 or 3. So here actually we are going to get 1, 1 and 1, 3 for possible values of mn. Now let's try m equals 3. If m equals 3, I will be getting the following. So the first one, from this one, I'll get 3 divides 2n plus 1. All right, 3 divides 2n plus 1. And from the other one, I'll get n divides 7. So it's a matter of checking this one first, because n divides 7, that gives 1 or 7. Now, we can easily verify that if n equals 1, this is going to be 3. So 3 divides 3, that's correct. And if n equals 7, this becomes 15. And 3 divides 15, so that's also correct. So n can be both 1 or 7. So with this, we can get that 3, 1 and 3, 7 are both possible. All right, and there we have it. We have these possible solutions. But we have to take note that we assume that m was the smaller one, so I can interchange the m and n here. So although we just see 4 solutions, this one is okay because that's already 1, 1. So reversing it also gives us 1, 1. And then this 1, 3 and 3, 1, those are reverses of each other already. And then lastly, this 3, 7, although it seems to be that there are no other solutions, because of the assumption here that m was the smaller one, we could also have 7, 3. All right? So in total, we should have 5 ordered pairs, and these are the 5. 1, 1, 3, 1, 1, 3, 3, 7, and 7, 3. And these will be our final answers. Hopefully you guys learned something new from this video, and I'll see you in the next one. Bye-bye!